Okay, hello everyone, and welcome to the performance and reliability session. Good morning, good evening, or good afternoon, whatever you are. We have a mixture of journal first and technical papers in this session. And as it has been the pattern throughout, each presenter will give a 5 minute presentation, and we devote the last 30 minutes for questions. I'd like to ask the audience and even the other authors of the papers to put your questions in the chat as the presenters present the papers. And after that, can have a discussion about the work. So I'd like to introduce our first paper and speaker today. It's Christoph Laber, and he's going to present us his work about predicting unstable software benchmarks using static source code features. And Christoph, you have 5 minutes as we discussed before. Thank you.
All right, thanks a lot. So you should see my screen now. So today I'm going to present my MZ Journal First paper, predicting unstable software benchmarks using static source code features. My name is Christoph Laber. I'm a postdoc at Simula Research, and this work was done while I was still a PhD student at University of Zurich. So in this paper, we focused on a particular performance testing technique called software microbenchmarks. They are somewhat equivalent to what unit tests are for functional testing. So similar to unit tests, they are also defined in source code. So you just write a benchmark, which is a function that calls whatever you want to benchmark. And then the benchmarking harness takes this function and executes it repeatedly for multiple iterations. And for each of these iterations, the benchmarking harness measures the execution time of the method. And what we then have as a result is a distribution of values that we need to handle. So this is different from unit tests where we have a binary answer, pass or fail. Whereas with software microbenchmarks, we have a result distribution that we compare to previous versions or different implementations of an algorithm. And the challenge that we focused on in this paper is result variability amongst the result values, basically. So in simple terms, we can have two scenarios. Either the benchmark has low variability or high variability among its results. And this can have different impacts. When we have a benchmark with low variability, we can be almost sure that it will have reliable performance detection capabilities. So whenever we detect a performance change, we can be sure that it's actually a performance change, so a true positive. While on the other hand, when we have high variability, we can have one of these two scenarios, for example. So one can be that we do not detect a change, although there should be one because it's masked by the variability, a false negative. Or we detect a change, although there should not be one, a false positive. And whether a benchmark has low or high variability is hard to figure out before we execute it. So it only becomes evident after the execution and we look at the results. And it's always bound to a specific execution environment. So that means the same benchmark can have low variability in a very controlled environment, whereas it can have very high variability in an unreliable environment, such as the cloud. What can we do so far? Well, we can execute the benchmark for as many iterations as necessary to get stable results. But in our paper, the idea is that we take the benchmark in its representation in source code, feed it into a binary classification model that was trained on executions of other benchmarks in a particular environment, which then tells us whether the benchmark is going to be stable or unstable without the need to execute it. And for this, we take the following instability prediction approach. Imagine we have a benchmark from which we construct a static call graph, which gives us then a set of reachable functions. And with AST parsing, we extract different features from the source code of each of these reachable functions and the benchmark itself. In total, we extract 58 different features related to meta information, programming language features, and standard library API calls. And the main idea here is that we extract features that can serve as a good proxy for performance variability. And this is all inspired by previous research. What we then have is we have the feature counts of the benchmark itself and a combination of all the individual occurrences of all the reachable functions, so the code features. We then feed these two sets into the machine learning model, which tells us whether the benchmark is going to be stable or unstable. What we did is we evaluated this approach on over 4,000 individual benchmarks written in Go, for which we extracted the features and also computed whether they are stable or unstable. And for this, we looked at different numbers of iteration with which we ran the benchmark for, and at different thresholds of what decides whether a benchmark is stable or unstable. We then trained multiple models based on 11 different machine learning algorithms. And with these models, we answered two research questions. On the one hand side, can we even predict performance based on the statics features? And for research question 2, we looked at feature importance of individual features and feature categories. What we find is that for research question 1, that yes, we can predict performance based on static features, and we get the best prediction performance of 0.90 area under the curve and 0.61 Mathieu's correlation coefficient if we train the model on the highest threshold that we looked for and the largest number of iterations, and when using random forest. In terms of research question 2, we found that only 7 of the 58 different features are individually important, but all code features are collectively important for good predictions. And with this, thank you for your attention, and I encourage you to read the paper and look at our talk that is on YouTube. Thanks.
Thank you very much, Christoph. That was bang on time. And I'd like to ask our next speaker, Sophia Quach, that is going to talk about the impact of falsely detected performance inducing changes in JIT models. And as questions arise, please put on the chat, please.
Okay. So hi, my name is Sophia Quach. I'm presenting my work on evaluating the impact of falsely detected performance bug-inducing changes in JIT models. I worked on this during my master's at Concordia University, and it was a paper accepted at MC. So SEZ is very popular and it's been discussed and used in many papers, and in an ideal scenario, it can identify the exact changes that introduce a bug. So in this ideal case, we consider the results to be changes that were identified by the SEZ approach that were truly bug-inducing commits, or known as true positives. So SEZ is used a lot in code review, fault localization, and in JIT defect prediction. And it's to know whether or not a change introduces a defect. JIT uses the SEZ approach, which links each defect fix to the source code change introducing the original defect. It does this by combining information from the version archive with the bug tracking system. And our work in the paper focused on studying JIT performance-related bug-inducing changes and how they impact the performance of JIT models, as well as on the data itself that's produced by the SEZ approach, which are the bug-inducing changes detected by the SEZ approach. So in a prior study, we found that SEZ has low accuracy for non-functional commits. So in this paper, we ask ourselves if the extremely low accuracy on performance bug impacts JIT defect prediction. So we have 3 RQs. In the first RQ, we ask how well can JIT models predict performance bug-inducing commits. So similar to prior work from Kame et al., we consider 13 factors grouped into 4 dimensions to filter out our data. In our paper, we built random forest models as our JIT classification models. And due to the imbalance of bug-inducing and non-bug-inducing commits in our data, it's suitable for us to use random forest trees to not overfit the models on non-bug-inducing commits. We also explore other models that could be used that are mentioned in the paper. And now we find that although the AUC score for performance bug-inducing commits is very high and much more than bug-inducing commits, we realized that the ground truth is wrong because we hadn't verified the performance data. And these are the details for the random forest. The values for other classifiers are included in the paper. So we make an extra step where we manually identify and fix the wrong results from the SEZ approach. So at the bottom, you can see the AUC measures are much lower when using the verified performance bug-inducing commits. So from RQ1's result, we can see that the wrong results on SEZ did make a big impact on the model. So in RQ2, we want to see if one can correct such results from SEZ and whether the model can perform better using that as a training data. So now we use the manually verified model in the training data, the manually verified data, sorry. So we see that the AUC score is increased after we correct the wrong results from SEZ and using the correctly labeled results to build the model. And the AUC values are in pretty good range. However, it's still much lower than the AUC values for non-bug inducing commits. And so in RQ3, we think maybe the nature of performance bugs and other bugs are so different that it makes no sense to put them into one model, and that might explain the difference in accuracy and prediction. So we were thinking maybe we can build a separate model, but just for performance bugs. So we built a variety of models. Each one has details in the paper, but we find that including all the data still appears to be the optimal solution for now, which is shown in model perf and non-perf, where the training data is comprised of X-1 performance bug-inducing commits, the non-performance bug-inducing commits, and all of non-bug-inducing commits. And that was my work. So thank you for your time, and I'll be happy to answer any questions.
Thank you, Sophia. So, can you please ask for those putting questions on the chat to put the name for who you would like to ask the question before the question. Thank you. Our next talk is entitled Using Reinforcement Learning for Load Testing of Video Games, and will be presented by Rosalia Castano.
Yes. Okay. I hope you can hear me and see the slides now. So hello everyone, my name is Rosalia Tufano and I'm a PhD student at Università della Svizzera Italiana in Lugano. So today I'm going to present you the work using reinforcement learning for load testing of video games, in which we propose an approach to support game developers in the testing phase of video games. More precisely, we investigated the possibility of using reinforcement learning for a specific type of game testing, that is load testing. Load testing is the process of stressing the game and measuring its response, searching for possible performance issues. And in this work, we focus in particular on a specific type of performance issue experienced by gamers, namely parts of the game exhibiting drop of frame per second, making thus the game less fluid, like in this GIF. So what happens during load testing is that humans play for hours trying to identify such areas of the games that we call here low FPS points. And this activity requires a smart interaction with the game because we need to advance in the game in order to be able to test the entire game environment. So to reduce the human effort in this expensive activity, we propose to replace the human tester with a smart agent trained to play the game as a human tester would. To build such an agent, one of the options is to use reinforcement learning, that is a machine learning technique based on the simple idea of trial and error. So in reinforcement learning, we have an agent interacting with the environment with a precise goal. The agent can perform some defined actions in the environment, and based on the performed actions, it receives a reward. The reward related to the agent's goal, and it is a sort of feedback, like a score about how good the agent is performing in the environment. So at the beginning, the agent tries to performing some random actions, then try by try, observing the rewards, it learns how to properly act to reach its goal. So we propose Reline, an approach that exploits reinforcement learning to support game developers in the load testing activities. So we have three main blocks: the game, the reward function, and the reinforcement learning model that represents the agent. So the game provides the reinforcement learning model with a representation of the game state in the current moment. It can be, for example, the screenshot of the monitor. Then the reinforcement learning model, based on the game state, decides which action to perform and send this information to the game. The game executes the action, the chosen action, and provide the reward function with two kinds of information. Game information that can be, for example, the current score in the game that helps the agent understand how to play the game. And FPS information, so the time the game takes to render the next frame after the chosen action, that helps the agent learn how to identify these areas of the game, so the low FPS points. And then the reward function, using this information, compute the reward and send it to the reinforcement learning model. So we evaluate Reline on a 3D game, 3D open source game, Paradox Kart. It is a kart game in which the player has to drive along the track and reach the finish line. So to evaluate our approach, we compared the agent trained with Reline with a reinforcement learning baseline, meaning that the agent in this case was trained just to play and win the game, and a random agent that simply performs some random actions. And here we have the results about how many low FPS points each agent was able to spot. So Reline found the highest number of low FPS points, but also the random agent was quite good, better than the reinforcement learning baseline. But the problem with the random agent is that since it is not able to play, it finds low FPS point in the first part of the track only. And moreover, sometimes it goes and spots low FPS points in areas of the game that are unlikely to be explored or considered by a human player. So with this, I conclude my presentation, and thank you for your attention.
Thank you very much. Some people were saying that my sound wasn't so good. Still, I hope it's much better now. I'm speaking closer to the microphone. Our next talk is called Eagle, Creating Equivalent Graphs to Test Deep Learning Libraries. The speaker will be Jianan Wang.
Yes, thank you. I will share my screen soon. Yep, screen now. So hello everyone. My name is Jianan Wang. Today I will present our work, Eagle, creating equivalent graphs to test deep learning. Deep learning systems have been widely deployed in many applications, such as self-driving cars, machine translation, and cancer detection. As a result, the reliability and security of deep learning systems are of vital importance. However, it remains a challenge to test deep learning systems, as deep learning systems are often complex and it's hard to know the expected results. Recent researchers focusing on using differential testing to solve this. The idea is to provide the same input to different implementations of the same functionality. More specifically, given a bunch of input, we feed them to two different implementations of the same functionality. And eventually, we compare the outputs of the two implementations to check whether there are inconsistencies. Here, inconsistencies represent implementations. To utilize differential testing method to test, Existing techniques test a pair of deep learning libraries to cross-check two implementations of the same functionality. However, there are two limitations. First, those techniques require at least two implementations in different deep learning libraries, which is often unavailable for many deep learning software functionalities. For many functionalities that only exist in one library, existing techniques. Second, they require a high-level library such as Keras to switch across deep learning library backends. Such a high-level library is hard to develop and maintain, and Keras has stopped support different deep learning libraries. To address these challenges, we propose Eagle, which uses equivalent graphs, a single deep learning implementation. Now, let me introduce a motivating example of using Eagle to detect a real bug in TensorFlow. In deep learning libraries, recurrent neural network functions, or RNN functions, can often accept two input formats. A common format is the first dimension represents and the second dimension represents time steps. This format is called batch measure, and it is the input format developers use. The other format, time measure, is time steps in the first dimension and batch size in the second dimension. The time measure format better fits RNN computations because RNNs compute batches step by step. Given two instances of three-word input, I like dogs and I eat apples, the input can be fed to RNN in batch measure format, I eat apples, or time measure format, I like it, dogs apples. Inspired by these two input formats, we can build a pair of equivalent. Suppose initially we have the same time measure input. We can directly feed it to the bidirectional RNN function with time measure parameter set to true. Or we can first transpose it to batch measure format, then feed it to the bidirectional RNN function with time measure parameter set to false. And at last, transpose its output back to time measure format. These two outputs should be equivalent. However, if there's implementation for handling one of the graphs, the output may be different, then we can detect inconsistency. In our experiment, we apply Eagle to test 13 RNN functions in TensorFlow and PyTorch. Eagle detects that all bidirectional RNN functions in TensorFlow incorrectly implement the time measure functionality. This bug is confirmed and fixed by TensorFlow developers. Here are our contributions. We designed 16 new tools, which cover 6 categories of deep learning graph equivalence to test deep learning libraries. We propose a novel idea of using equivalent graphs to detect bugs in deep learning libraries and implement the idea as Eagle. We evaluate Eagle on 5 of the latest versions of the most popular deep learning libraries, TensorFlow and PyTorch. 25 bugs, including 13 previously unknown bugs. For more details, please read our paper. Thank you.
Very much. Our next speaker will be John Hartman, and he's going to talk about decomposing software verification into off-the-shelf components, an application to SIGA.
Hello, everyone, and thanks for that introduction. As the title suggests, we are talking about SIGA, which is a schema for software verification, and as well, in general, on software verification. And this is joint work with Big Wire and Thomas Lemberger from LMU and my supervisor, Heike Werhan from University of Oldenburg. So, as I'm not sure if everybody is familiar with the idea of SIGA and software verification in general, let me give you a brief introduction. So in software verification, we have a task, which is a program and a property, and we want to know, does the program satisfies the property or not? And SIGA is the idea of doing this in an iterative way with refinements. And the first part of this SIGA schema is what we call abstract model exploration, which generates an abstract model of the program, for instance, using predicates so that some variables has a certain value, and then exploring only the abstract model. for bugs or for potential counterexamples. And if the abstract model exploration found such a counterexample, SIGA needs to check if this is really feasible, because we computed an abstraction in advance. So we need to check if the counterexample only exists due to the abstraction or because the program is really incorrect, which would lead as a final result. And if we find out that SIGA finds out that the counterexample is in fact infeasible, then we have the part which is called precision refinement, which generates a new precision, which guarantees that the counterexample cannot be found for a second time. So at least this specific counterexample, which is then given to the model exploration again, and the cycle starts again. So this is really, really used in different flavors and in different tools. But the issue we realized is that each tool realizes this SIGA schema with all these three parts in a stateful manner in one tool, which means we only have internal exchange formats, and information are exchanged on internal data structures, which makes it hard to replace one component. So just imagine if you have, for instance, an idea for a new precision refinement. One of the default ones is Craig interpolation. And if you think, okay, I read about Newton refinement, which is different, I want to try it out, then you need to re-implement everything, at least this precision refinement component in your tool. Or even worse, if you have an idea for a tool, or for one part, you need to build a full tool around that. So, which means if you have a new idea, then you need a new implementation. And the question we answered in this paper is, can we decompose that into loosely coupled components? And as a small spoiler, the answer is yes. So what we do is, or what we present is CSIGA, so component-based SIGA, which now consists of three components: the abstract model explorer, the feasibility checker, and the precision refiner, which communicate only via clearly defined interfaces, which are realized using existing GraphML XML exchange formats. So these are now violation witness, path witness, and invariant witness, which contain the information on the potential infeasible counterexample, the infeasible counterexample, and the precision increment. Why is this good? Because now we are able to use off-the-shelf components, which mean if there's for instance, new precision refiner which implements the Newton refinement I teased before, you now can just replace it due to the stateless design and the modular design with just a few lines of code, and you can use the off-the-shelf tools directly, which is due to the realization in the tool called, or with the technique or tool called QueryTeam, which allows this easy exchange. So if you want to use a new tool, it's really just 2 lines of code. And then you can play around with something new. So in the evaluation, we ask ourselves, is this concept really good? Is it a good idea to decompose something? And first, we just had a look on the overhead of component-based design, where we assume that we have information, non-information loss if we use the exchange formats. So we used exchange formats, especially for the invariant witness, which guarantees that we have no information loss. So we take one existing schema and the CPA checker, break it down into 3 components, and then let them run a standalone. And we see that the effectiveness is almost not influenced, so it just takes a little bit longer, meaning the efficiency decreases by a constant factor of around 3. So it takes roughly 3 times as long, because you now have 3 components, each communicate with each other, so you have I/O overhead. You need to recompute things, but you can solve nearly all the same tasks. And if you use, that was the second research questions, if you use standardized formats, then we see that the effectiveness reduces by around 20% compared to the one with perfect exchange formats, because some information are not encoded anymore. But the efficiency is not influenced, so it doesn't matter which exchange format you are using. And as teased in the beginning, we ask ourselves as a third question, does it pay off to use different components? So therefore, we used in total 6 combinations with 3 different feasibility checker and 2 different precision refiner. And it turns out, yes, you can solve some additional tasks. For more information on that evaluation, have a look at that paper, please. So let me sum this up. CSIGA, or component-based SIGA, breaks this tightly coupled SIGA version into smaller standalone components. So defines the components and explains how to break it down. And we show in the evaluation that this really pays off. So we have a similar effectiveness as the tightly coupled version, and we get an improved effectiveness using different techniques. So we can conclude decomposition in software verification pays off. If you want to try that out, have a look on the artifact, which is available at that link and also linked in the paper. Thanks for your attention. I'm happy to answer questions later.
Thank you very much, Jan. And our last speaker is Yuyan Guo, and he's going to talk about precise divide by zero detection with affirmative evidence.
Okay, let me share my screen. Hello, everyone. My name is Yuyan Guo. I'm happy here to share our recent research on precise divide by zero detection. Divide by zero is a common programming error. It happens when performing the division instruction with a zero divisor and can lead to undefined behaviors, such as crashing the system. Over the past 5 years, there are more than 90 CVEs related to divide by zero bugs. There are many ways to catch divide by zero bugs, including dynamic analysis and static analysis. In this talk, I will focus on the precise static detection of divide by zero bugs. The motivation of our research comes from our experience of deploying representative static analyzers in detecting divide by zero. We observe a high false positive rate of over 70%. So we are curious about the underlying cause of this unsatisfying precision. Conventionally, static analyzers detect divide by zero by finding an execution path that ends in a division instruction. The static analyzer then encodes the path condition into PC and conjunct it with the error condition for the divisor variable to be zero to formulate the final constraints. If the final constraint is satisfiable, it will choose to report a divide. However, in real-world programs, there are many unknown factors to static analysis. For example, V may take the value of some unmodeled library calls. The computation of V may involve including inline assembly. In such cases, the variable can be under-constrained in static analysis. If such under-constrained variables are present in the final constraint, it can lead to massive false positives. The key insight of our approach is to attack the divide by zero detection problem from a different angle. Instead of reporting a bug whenever safety verification fails, we can try to actively find evidence in the divide by zero bugs. Here, evidence means extra information on these under-constrained variables that can contribute to improving the precision. Let me use an example for illustration. For the 3 functions shown here, the variables x, y, and z are under-constrained in static analysis. Also, notice in these functions cannot rule out the possibility for triggering divide by zero. Therefore, in the eye of a conventional static analyzer, all 3 functions are susceptible to divide by zero bugs. However, our approach will only consider the program and the write program as potential to trigger divide by zero bugs. In the middle program, we can observe that the program compares the variable x against y. This suggests her beliefs that x is y. If such beliefs actually hold, x minus y must be 0, so there is a divide by zero bug at the return statement. For the write program, since x comes from tainted input, it can take any value, including the 0 value. Therefore, the write program will trigger divide by zero bug. More specifically, we say that we have identified a bound evidence from the numerical comparison statement from the middle program, and we have identified a source evidence for x to be tainted from the write program. And our approach will only report a divide by zero bug if we can to support its bugginess. During an empirical study of 87 CVEs caused by divide by zero bugs, we have found out that 74% of them have evidence. This suggests that our evidence-based idea do capture considerable real cases. Our approach is a propagation algorithm. We first construct an augmented data dependence graph from the program, and we will apply a guarded value set symbolic domain to encode the numerical relations among variables. Then evidence is generated and propagated from the data dependence graph, and bug reports are deduced by resolving a set of constraints from over the symbolic domain. Implemented this idea in a tool called Read based on LLVM, and we have found 14 new confirmed divide by zero bugs with a low false positive rate of 22%, significantly outperform existing works. That's all of my presentation, and I'd be happy to take questions later.
Thank you very much. At this stage, I'd like first to thank all the presenters and clap for all the nice presentations. We are now open for discussion and questions. Please put your questions on the chat or try to come up on your video and ask questions directly. I'm going to go through the chat now and see if we already have some questions. I believe we have a first question that is from John Halterman, one of the presenters. And this is for Christoph, John. And I think Christoph tried to answer, but perhaps we could answer to everyone instead of writing in the chat. So can you name the 7 features that are relevant in your approach, please?
No, absolutely, I can. This depends. So some of the 7 features, so 4 of the 7 features are related to just the benchmark code itself. So extract from the method of the benchmark, and these are mostly related to meta information, lines of code, and 5 lines of code where the benchmark is located in, and the number of bytes in the package, as well as nested loops in the benchmark. And the other 3 are related to the code that the benchmark calls, so from the call graph, basically. And here we have synchronization API calls, such as mutex, locks, unlocks, etc., dynamic arrays, and also nested loops. But one thing that I want to stress here is just because these are the only 3 relevant features doesn't mean that we can only rely on those 7 for the good predictions. Because I suppose by the way that how permutation feature importance works, that there is an interplay also between different features and feature categories that we did not test for that provide the overall good prediction performance. But
at least for the first 3 or 4 factors, it means the larger the file gets. So that would be my naive interpretation of that. The larger the file gets, the more it may influence this, or.
Well, I mean, it may. That's exactly the correct word, because we have a correlation and not a causation here.
Yeah.
So it might be an indicator, but it might not be the reason why they become stable.
Okay, and did you also look at something like so nested loops make of course sense. Do you have any insights on if the loop is bounded or not? Because I experienced that this might also be a factor if we have it bounded or unbounded. So if we have random or non-random loop bounds.
No, unfortunately, we did not extract loop bounds. I can see why it can have an impact on the wall clock performance. So if you have an unbounded loop that it just takes longer to run, I'm not so sure whether it will equally have an impact on the variability of the results. So these are the 2 things we do not have to like confuse the runtime and the variability of repeatedly measured runtimes.
And how much so is there any randomness involved in the benchmark, or is it
potentially, yes. I mean, we also look for IO, random number generators. Yeah, I don't know, like a thread scheduling might have an impact. So there are multiple factors that could have a random that introduce randomness into benchmarks, obviously.
Okay, but the benchmarks are in general fixed and not rely on random functions which are called all over.
I mean, Not that I know of, but it's also, I haven't checked all 4,000
Yeah,
benchmarks individually, so I'm sorry, I cannot like give you that.
No, that's absolutely fine. So I'm using benchmarks where we have random function calls all over the place. That's why I'm asking.
Okay.
So they are, yeah. But thanks for that answer.
Thanks.
And the answer.
Thank you. Our next question came from me to Jianan about the 16 rules that you use. If you can give us more information about the rules. I know you wrote some things in the text, but perhaps to share with the others in the audience.
Okay, so we have the 16 rules in our paper. So the 16 rules are we manually defined by examining the API, the deep learning API documentation, and examining the GitHub issues of TensorFlow and PyTorch. And some example of our rules. For example, we have the rule, which states that the computation of any API should be equivalent with or without optimization. Another rule in that structure equivalence states taking dense tensors should produce identical results to the same function or its sparse version taking sparse tensors. So, and also the motivation example I explained in the talk is also a rule states, the RNNs taking time measure input should produce identical results to the batch RNN taking batch measure input and add transpose to their input and output. So that's some examples.
Okay, thank you. There is a question from Doreen Tomian, and I think this was for our last speaker. What's the current state of the art for division by zero problem?
Okay, I can answer this. First, we have a sound verification approach that tend to verify the correctness of this program. But this work focuses on bug detection, so the method is not sound. And for bug detection in our paper, we actually compared it with the symbolic execution approach representing plan static analyzer. And the analyzer in Facebook Infer has a divide by zero checker, but its algorithm is not documented. But I believe we are the first to identify and discuss the precision problem in divide by zero detection. So that's the answer.
Okay, thank you.
Okay.
Johan, I have a follow-up question. Do you think your static analysis approach can be used for other types of bugs?
I think the precision problem can be seen in other types of numerical bugs like integer overflow or static buffer overflow. So I'm currently working on the static detection of other numerical bugs.
Okay, thank you. We have a new question for Rosalia from Christoph. Can a game developer use your approach to reproduce the low FPS scenario and debug the problem?
Thank you for your question. Yes, because when we run this test from the agent, we record all the actions and all the measurement of the frame rate. So yes, we can reproduce the bug and the developer can understand if there is a problem, where there is this problem. We can also provide a sort of report of all the bugs or this area of the game that the able is able to spot. And so using this, the developer can understand where is the problem.
If I can, I might have a follow-up.
Yes, please.
So how reproducible are the bugs that you find? So if you actually replay the sequences that your approach does, do you always get the same frame rates at the same point?
Yes. In fact, before to start, we we wanted to be sure that our measurement was reliable. And so first of all, we ran all the tests, all the training in an isolated server. And after that, we also run a test in which we have one agent that is just able to play. And we let it play 300 of identical games. So this means that the agent play every time the same exact game, so the same actions. And so we found that the trend in each game was the same. I also have a graph here if you want to see it. If I'm able to show it, sorry.
But I think you had the graph in your video on YouTube, right?
Yes,
So
yes, exactly. Yeah, but no, sorry. It's not this one. Okay, I'm not able to find the presentation anymore, but yeah, it's on the full video and also on the paper, right? Is this one. It's a bit small, but yeah. So these are 300 identical games, and here we have the actions on the horizontal axis, and on the vertical axis, the time that the game takes to render a frame in milliseconds. And so you can see that the trend is the same.
Okay. All right, thank you.
I would have a follow-up question on that.
Yes, please.
So how complex would it be for others to use your approach for different games? So how much engineering work is it to generate all these data? And is it just like click and play, or do I have to manually do a lot of things in the background?
Yes, this is an interesting question. Thank you. Well, for sure, you have to change the reward function because it is based on game, of course. But one thing that is interesting here is that we used like reinforcement learning. We have a convolutional neural network. So this means that the agent sees the screen of the game and then it learns how to play watching the screen. But we did this to generalize this approach. So in this way, you can use any game you want. But to speed up the training, it is better to use different informations that are based on the game. In this way, you can speed up the training and get faster results. So
Okay,
yeah, you can, but you have to modify some things.
Yeah, that's for sure. Thank you for that answer.
Thank you.
Thank you. I think we have another question for Jenna. About the rules again. Since the rules are identified by existing issues, i.e. bugs in GitHub, I am wondering how is Eagle's performance in detecting new bugs?
So Eagle detects 25 bugs in total, and among them, 13 bugs are new bugs that are known bugs, and 9 of the 13 bugs have been confirmed by the developers.
Okay. Is Meizinuli satisfied or wants to elaborate more? Okay, thank you. Any more questions? I think I had a question to John. I know it's in the paper, but perhaps to give us a better idea during the discussion and presentation here about the data set that you use in your evaluation.
Yeah, so for the evaluation, we used the data set from the software verification competition, which is held annually. And it's around 8,500 C programs that need to be verified. And the SIGA approach is, to give you a rough estimation, is able to solve around, if I remember correctly, around 4,000 of these. And that's the data set we're working on. So then we say it gets each approach has a time limit of 15 minutes. And in most of the cases, it's much faster, but that's the overall timeout. So that's the data set we are using.
Okay, thank you. Any more questions from the presenters or from the audience?
I have a question about the CSIGA paper. So is this approach have a prerequisite that those verification tools use the same program IR? Is that a common scenario in the verification community?
So no, they don't have to use the same representation of the program, but what we require is that they produce the same output results. So the competition requires that each tool produces a violation or correctness witness and puts a lot of information in that. And you can generate, so in a prior work, I had a look on tools which only work on the LLVM language and forget about C. And you are able so if you're able to get the information for LLVM, so for instance, if you find interpolants in LLVM, if you're able to trace them back to C, then you can generally use any tool. But you need so the formats are talking about the C program, and hence your information in the end has to be on C program, on the C program level. So you need to give new predicates in form of C variables. So you cannot use the LLVM variables because you're not guaranteed that the next tool uses LLVM. So thereby we don't fix it to a certain intermediate representation. But yeah, if your tool is doing a lot of optimization, is generating a lot of intermediate things, then this tracing might get a little bit more complex. But technically, that's somehow doable.
Oh, thank you.
Thanks for the question.
Thank you. Any more questions?
I can ask one to Sophia, maybe.
Yeah, good.
So in your paper, what do you consider to be a performance bug?
So I have an example I can show you. Give me a second, I'm going to look for it. Maybe someone can answer a question while I look for it. I need a few minutes.
Okay, while we wait for Sophia to find the example she wants to show, I'd like to follow up with a question to Rosalia. Why reinforcement learning? Why did you decide to use this technique?
Well, we decided to use reinforcement learning because we have seen in the literature that it is very well suited for games. In fact, we can see that they reach very good results in using reinforcement learning agents to play any kind of games, starting from very simple games like Atari games, and also for very complex, I don't know if you know these games, but like StarCraft, or also Skaki, or also Go, in which we have a space of possible actions and status of the game that is very big, and these kind of agents performed very well. So we thought that it can be one of the best options. But of course, we tried only reinforcement learning, so I cannot be sure that is the best one.
Okay, thank you.
And of course, you need a smart interaction with the game, because you have to learn how to play. And so a different agent that does not make a decision on the how to play, how to advance in the game, can be a problem.
Okay, thank you, Rosalia. I think Sophia is trying to put some answers on the chat, but maybe you could elaborate, Sophia.
Yeah, so I attached a screenshot of the performance box. So the red part was where they had seen it as a performance bug, and then the green part is to fix it. So it was that they found that the for loop in the red portion would take more time and performance as used in the green one by using the hash function of Merkle trees, which is less expensive.
So you take the issue tracker as your ground truth for
Yep.
reported performance bugs.
Yeah, the issue tracker. The Jira issues.
Okay. Any other question?
I have a question for the first paper. Do you have any ideas where, if we consider the program is evolving, so the source code may change? That whenever the source code change, if we apply this method, we need to retrain the whole thing, right? So how maybe the code features may not be applicable if the code evolves. Do you have any ideas on this problem?
Yeah, so we did not look at it in a regression setting, so over software evolution. We only looked at it at one particular snapshot of the program. So I cannot give you like a definite answer of how often we would need to retrain it. But what we know, at least colloquially, is that the benchmarks themselves, so the code of the benchmarks themselves, hardly changes with software evolution. That is probably not true for the code that is called by the benchmark. I think this is all that I can tell you. But there is, I'm also not quite sure how relevant this is for like looking at evolution for the variability of the performance tests. I think it would be highly relevant for detecting performance changes. And there are quite a few works in this direction, and they look at certain related diff metrics like I don't know, added functions, removed functions, etc. But yeah, so this would definitely be something interesting to investigate, whether the variance of the benchmark results changes over the history or over the evolution of the project.
Okay. One more question. Maybe sometimes an unstable benchmark can be exhibit bug. That's just my intuition.
Yeah.
Stable benchmark.
Right. I completely agree. And we have in our paper, we have quite an extensive discussion on that, what we do with this information, whether a benchmark is stable or not. And so one of these potential application scenarios would be a sort of a regression test selection or whatever of only stable benchmarks. But then what again do you do with a test that or a benchmark that covers your most important part but is unstable, or is just unstable based on on what it is testing? Then you could not remove it. So I completely agree, and this is a very good observation. But I also don't have a solution for you. I'm sorry.
Thank you. Thank you.
Good. I think we are reaching the end of our session. I would like once again to thank all the presenters for very interesting and thoughtful papers. And I hope you enjoy the rest of the conference, and we may see each other again in one of the social events and